Welcome everyone. We are Team TriForce Analytica. We are Elijah, Hengly, and Magnus, student in master degree in data science program. Our logo is on the edge left corner. Our project title is Leveraging Machine Learning for Advanced Crime Prediction in Los Angeles. Today, we are presenting Chapter 4, the result with tuning, and Chapter 5, conclusion and future work. This week for our project update, we are sharing what we found after making adjustments to our models to get better prediction, along with our final thoughts. We revisit our three main questions and explain how we fine-tune our models. We show you how our models did after tuning by looking at some key performance number and comparing them to how they did before. Our team will explain how this tuned model help answer our three big questions. A key part of our result is showing you how this adjustment improve our predictions. To wrap up, we talk about our conclusion and what we think for the future hold for projects like this in predicting crime. Start with our main question and how we approach them with our models. For our hypothesis 1, we look at crime hotspots and when they happen. We are predicting the number of crimes on any given day. Using two-time series algorithm called ARIMA and LSTM, we expanded our work from 10 to 44 different models, focus on each area and the whole LA as another area. Then the hypothesis 2 and 3, we explore if weather plays a role in kind of crime that occur and how much who the victims are can tell us about the crime pattern. For this, we're looking at the type of crime and predicting which one are likely. Initially, we used 6 different techniques, but narrow it down to 4, leaving KNN and linear SVM out. We're still using the same way to measure how well our models are doing, such as accuracy, precision, and F1 score, and log loss, etc. The grant category variable is our target variable, which was reduced from 144 to 8. Hence, we have 8 main crime types. Model 1 includes all relevant predictors. Model 2 excludes only weather features. Model 3 excludes only victim demographic, whilst Model 4 excludes both weather and victim demographic features. With the 16 models we built, we tune with hyperparameters, increase, decrease parameter, and all the result we got is lower than 29 accuracy. But by adding time occurrences to be part of the predictor features, we got a better result, which is 81, which is better. We also check any multicollinearity as well. Next, I will pass it over to Magnus to talk more about time series algorithm.
Hello everyone, and thank you, Hengly. To provide a more granular prediction of crime hotspots in Los Angeles, we look at the 21 areas individually and the whole city of LA as one area, which makes a total of 22 areas. While the average daily crime incidence in LA is 37, we can see from the chart on the screen that there is an average of 53 crimes per day in the 77th Street, making it the area with the highest crime rate. With 44 crimes, Pacific area ranks second in average daily crime incident rates. We can see that Hollenbeck area has the least average crime incidence of about 24 crimes per day. It, however, did not produce the least total number of crimes, as that went to Foothill. And so we ran 44 models, 22 for ARIMA and 22 for LSTM, and we came up with the results as you can see on the screen. The Los Angeles citywide area, which is the total area, had an ARIMA root mean squared error of 27.57, while the LSTM root mean squared error was the 16.55, showing the LSTM to be superior in terms of performance levels. For the individual areas, we can see that ARIMA had an average root mean squared value of 24.4 with a low of 7.05 for the Hollenberg area and a high of 40.33 for the Pacific area. LSTM, on the other hand, average root mean squared error values of 2.21 with a low of 1.69 for Hollenberg area again, and a high of 2.65 for Olympic area. The lower the root mean squared error, the better the model performance of predicting crime occurrences. LSTM outperforms ARIMA across all the 22 geographical areas, as you can see on the right-hand side of the screen. The LSTM prediction charts are at the bottom of the slide, while the ARIMA prediction charts are at the top. On the left-hand side is the crime incidence prediction of the entire Los Angeles citywide area, while on the right-hand side is the Hollenberg area crime incidence prediction. We can see that the LSTM charts at the bottom are almost perfect. We can see the predicted data is almost mapping out with the actual data compared to ARIMA, which just shows you the linear green legend across the screen. So now I'm going to pass it over to Elijah for results on our crime categorization classification. Thank you.
Good evening, everyone. To continue on from last week, we were advised to remove certain models that were taking too long to train or performing poorly, such as k-nearest neighbors and support vector classifiers. Our 4 final algorithms we used were logistic regression multinomial, random forests, decision trees, and XGBoost. We could see a clear pattern in the 4 charts for each model's accuracy, precision, recall, and F1 score. The 4 different data sets allowed a total of 16 models to be trained to see how each performed in the presence of all data, no weather data, no victim demographics data, or missing both victim and weather data. When weather data is removed, some models show a very slight decline in performance, and some do not change at all. However, all performance metrics worsen visibly when victim demographic information is removed. So we did a thorough assessment of all feature importances, scaled a percentage, to see how the hypothesis variables were influencing model outcomes. In all cases, Webben reported Part 1-2 and time of occurrence were in the top 15 most important features for all models. When weather information is removed, performance parameters change minimally and other features become more important. So before we present our final results, we also created and merged our Chapter 5 into our main document. Some suggestions we made for future works are implementing these models in areas or regions outside of LA. Hybrid model building or data sets that are more feature inclusive could be used to train these models, since we only had victim information instead of perpetrator information, for example. So due to the sparseness of some location data with our data set, our hotspot analysis was limited to areas. But with more resolute location data, a more refined predictive model could be considered in the future. AI is making its way into crime prediction in ways like sound detections for things like gunshots, and even AI-controlled body cams, which are even used in Los Angeles now, as shown on the image on the right. So to conclude our first draft of our capstone project, we were able to prove 2 hypotheses to likely be true, while 1 ended up being likely false. Unfortunately, weather information did not appear to add good predictive value to crime categories. On a better note, there are clear trends in the impacts of victim demographics on crime types. Also, when training neural networks to perform time series analysis for crime amounts, a very low root mean squared error was achieved for several of the 21 areas using long short-term memory networks, showing future crime amounts can be predicted in the different areas of LA with reasonable accuracy.